Hello, I'm going to make this video sort of another example of how you could possibly make a video of yours for this project. More likely a sprint, not the final video, because this is a video of a slideshow and that might be a little bit boring. But if you want to include little snippets of something from a slideshow, one of the ways you could do that, I'm using Screencast-O-Matic. It's a free online, I guess, software. A lot of the teachers use Screencastify. You can also record your Zoom sessions, like create a Zoom meeting and record it. And there's also that Windows, the Windows button and press the G, like gamers do that. So there's multiple ways of recording your screen. And my favorite way is Screencast-O-Matic. So that's how I'm doing it. So this video is about the Rutherford's gold foil experiment, which you're going to use video data in order to actually do the experiment this year. In past years, I've had students do it before in person, or actually hands-on. But you might ask, what does this have to do with your need to know of nuclear technology or nuclear reactions? And I will tell you. So nuclear technology, or rather radioisotopes, were used to help us understand the structures of the atom. Ernest Rutherford had already discovered the existence of alpha, beta, and gamma rays and had proved these were the consequence of the disintegration of atoms in 1899. In 1908, he was trying to precisely measure the charge-to-mass ratio of alpha particles, which are tiny positively charged particles that are spontaneously emitted by certain substances such as uranium and radium, or radon also. In order to do that, Geiger, Marsden, so Hans Geiger and Ernst Marsden were students of Rutherford, and Rutherford designed an experiment where alpha particles would pass through a glass tube and be detected. However, this setup proved to be unreliable because the alpha particles were deflected by air molecules. That wasn't expected, that anything could deflect the alpha particles. They thought it would go straight through. This was surprising since according to the Thomson model of the atom, the alpha particles should be too heavy to be deflected by the air molecules. This brought Rutherford and Geiger to investigate how much matter could scatter alpha rays. From 1908 to 1913, a series of experiments carried out by Geiger and Marsden under the direction of Ernest Rutherford shaped our ideas about the nature of the atom and disproved J.J. Thomson's model of the atom. Thomson believed that the atom consisted of a positively charged jelly-like mass with a negatively charged electrons within it. So this is the positively charged mass in pink, and then you have the little negatively charged electrons. He called it the Plum pudding model. There's kind of a 3D rendition of what it might look in 3D. Oopsies. The experiments that Rutherford did involved bombarding a metal foil, which is right here, with alpha particles, which were emitted using a radioactive element, and observe how the foil scattered the alpha particles in relation to the thickness and type of material. They used a fluorescent screen to measure the trajectories of the particles. So here's the fluorescent screen kind of all the way around. So you know if the particles went straight through, straight back, or if they bounced and went in some other angle. Each impact of an alpha particle on the fluorescent screen produced a tiny flash. So they had to sit in a dark room, look at the screen, and basically make a note of all the different flashes. A very tedious experiment. For the metal foil, they preferred gold because they could make the foil very thin. They preferred the source of alpha particles was radon-222. They also used bismuth-214 and radium-226, but the radon was their preferred radioactive isotope. They bombarded a thin piece of gold foil with alpha particles, or helium nuclei. Then with the fluorescent screen, they observed that most went through the foil without changing directions. A few, however, were reflected back at acute angles. That means like almost straight back, really bouncing back. The relative number of alpha particles reflected at different angles was counted. By mathematical analysis, Rutherford was able to show that the scattering pattern was caused by a small positively charged center within the gold atom. Rutherford was able to show that this central nucleus contained more than 99.9% of the total mass of the atom and has a diameter of only 0.01% of the atom itself. Okay, so this is basically what the experiment looked like, with the red parts being with the alpha particles. They either went straight through, most of them did, which is this dark red line. Some of them were deflected slightly, and some of them were even deflected like almost right back, and that was very, very surprising. Here is a quick video of what it looked like.
The nucleus of an atom was first discovered when a beam of positively charged particles emitted from a radioactive source was aimed at a fluorescent screen. The particles caused the fluorescent screen to glow. When a very thin sheet of gold foil was placed in the pathway of the particle beam, a few particles were deflected to the side. Occasionally, particles were deflected straight back. But nearly all particles passed right through the gold foil, as if it were not there. The scientists concluded that atoms must be mostly empty space, and that because some particles are deflected, there must be a small positively charged central mass, which they called the nucleus.
Okay, so the takeaways of the Rutherford Atomic Model, or also called the gold foil experiment, were that the atom is mostly empty space. The nucleus has a positive charge and almost all of the mass. The nucleus is very tiny central core of an atom and is composed of protons and neutrons, and the electrons are distributed around the nucleus and occupy almost all the volume of the atom. So this is an image of our classroom setup, how we would do it in the classroom if we could. And the radon, or the alpha generator, which is radon, is the person who is rolling the alpha particle, which is a marble in our simulation here. So you'd roll the marble underneath this cardboard box, and the cardboard box represents the gold foil. Underneath here, where you can't see it, there is a small object that represents the nucleus of a gold atom. So this is basically the size of the gold atom from one end to the other. So you would roll the alpha particle to the target, which is this whole area here. And then you would observe whether the marble or the alpha particle goes directly through and doesn't hit anything underneath this cardboard, or if it does hit something and it reflects off in a different angle, right? So not going straight through. The video I have shows probably well over 200 throws, or 200 alpha particles going under this cardboard, and you are to determine how many actually hit the target or hit the nucleus and deflect versus go straight through and hit nothing but empty space.